Now we're on our third part. So we're going to talk about this time about filtering, enhancement, and feature extraction. So now that we have digitized them and represent them in a certain format through our compression process, now what do we do with them? Okay, so now that we have the files, so we can perform some filtering or some other enhancements, and even we can make use of feature extraction purposes or techniques for machine learning purposes. And yes, that's for AI na. Okay, so okay, this is another quite um, highly technical topic. So please bear with me. I'll try my best to speak in the simplest way possible that I can. Okay, so when we say filtering, we basically remove the unwanted components of a signal, and while we are doing that, we make sure that we preserve the useful information. Okay, so um, i- kumbaga, we are making some changes. We are um, most likely we are uh, cutting off everything that we don't want. Okay, but by doing so, we make sure that what we want remains okay. Okay, so we preserve whatever is useful. And this is actually the first step in pre-processing pipelines before extracting features for machine learning applications. So ito na. Actually, ang main goal naman po na talaga natin is to um, how before we can study technologies like computer vision and voice controlled natural language processing systems like what we have in Alexa, it's very important that you have to understand basic audio and video processing, hence this webinar. So filtering is one of the core concepts, and this is quite techy actually. So here a simple illustration of basic pa lang basic filters or um, for example, we have these signals, this signal, and it has these components. Kumbaga, if we dissect it, just like in 3-in-1 coffee, we'll see it has these components. Okay, so each of these can be can pass through these any of these filters. Okay, so in short, once we have our signal, if our signal goes through a low pass filter, then its lower components will be preserved, or meaning will be allowed to pass, and the rest will be blocked or filtered out. Okay, so will be removed. So the lower ones will pass, the higher ones will be blocked. Okay, so that's the opposite of high pass filter. So the lower ones, like this, the lower ones will be blocked, while the higher ones, higher frequency components, will be allowed. Now, if you want to select only a specific portion, just like this one, if our complex signal goes through a bandpass filter, it will allow only what's in the center or in the middle. So it will block the lower ones and also the upper ones. So only the middle part will be allowed. And we have the band stop or the notch filters opposite of the band pass. So here we allowed the lower ones and the upper ones, the higher ones, but not the middle ones. Okay, they are blocked. Okay, so this is the most basic essence of filters. So high pass, low pass, band pass, and notch. And then later, eventually, um, okay, we have some more advanced concepts in a few next slides. Okay, but for now, maybe you wonder, okay, filter. So is that the same filter with what we have in IG or in any social media apps, wherein we have our picture and we can simply select a filter, and then something something else comes out. we have a better picture or we have a worse picture. Okay, so basically, this is what happens in the case of images. So, kasi yung audio mas madali, 'di ba? For if you want to want our sound to have a lower frequency, meaning mas bass, want to enhance the bass, we have to limit the high frequencies, then we can have low pass. Or if you want the opposite, if you want the higher ones to be more emphasized, then you can have the high pass and things like that. So that's for the audio. It's easier to conceptualize. But in the image, it's quite more complex. So here we have um, 2D convolution. So what happens here actually is a convolution process. So I'm not going to talk about convolution, but I'm just introducing the term 2D or two-dimensional convolution. So this is what 2D convolution and process looks like. Okay, so this is how our filter works. So for example, each filter that we have in our apps, social media apps, for example, have a certain kernel. So that kernel is basically a two-dimensional filter. So like this. So in each filter, my combination of values here in a kernel. So that kernel is being something like being white around our image, starting from the top to the right and then up to the bottom. Top left up to bottom right, like that. So one by one. So each step, as you can see, there's a corresponding new value, meaning this is the output of our uh, filtered output of our image. Once we apply this filter, so it's like you're wiping your filter around. So that's what our system does. Okay, to come up with a filter. So the filter, just like here, um, it enhances some parts, it blacks some part or filters out some parts depending on this kernel. Kernel basically image filter. Okay, so that's 2D convolution without the math. Okay, so next, a few more advanced concepts. I didn't put labels anymore, so let's see how how it goes. Okay, so here, um, when we are filtering, just like what I mentioned earlier, it would be better to see the frequency components of your signals before you apply filters. Just like here, this is the waveform, the time domain version or representation of your signal, while the upper one is the three-dimensional spectrogram. So you can see the waveform on this view and then the components on this view. Okay, so here this like yellow board serves as the cutoff. So when we are filtering, we are actually doing something like this. So we are selecting which part do we want to cut off. Okay, so just like this one. Okay, the red ones, I think that's the noise, the original version of the signal, which is noise C, and we want to get rid of the noise so that we can recover the original, the message that is inside it. Okay, so medyo na pinutakte na ng noise yung signal natin. So that's why we make use of a filter so that okay, we can remove the red ones. And if we have a filter, we can have a shape like this so that everything our filter should have a shape like this. Okay, depending on your analysis, so that everything else will be cut off. Okay, so I hope na conceptualize na natin. Okay, so when it comes to audio, basically just like I think most phones have equalizers like this. So we select the frequency that we want to emphasize, to boost, or to lower down or de-emphasize. Okay, so in effect, this is what happens. So we can have different shapes of filters. Now we have more complicated shapes. Okay, and later on, how do we do that? Well, we're going to have a very brief overview of how do we come up with these complicated shapes. That when we adjust the frequencies and the gains, we get to have these shapes. Okay, more complicated shapes of um, of our spectrum. Okay, so but before that, we have to understand a few terms. So in the frequency domain, this is example of our low pass frequency response of our filter. Our filters are analyzed in terms of frequency response. Um, or one way we analyze filters is in terms of frequency response. Um, Here, of course, the higher the amplitude. Um, our frequency response is composed of three portions. The pass band, that's where our signals can pass or allowed to stay as is. The stop band, that's the portion where they are cut off. Okay, we remove them if they fall here. And in between them, we have the transition band. And take note that we don't want transition band because we just want either we pass them, we allow them to pass, or we block them. So transition band is something alanganin. It's something no, there's no assurance. We can something unpredictable whether these portions can pass or not, or if they can pass, they are attenuated at some points. So ideally, we don't want transition band. There should be no transition band. But in reality, we cannot do that. Okay, there's always a transition band, and what we can do is only to minimize it as much as we can. Okay. However, the more we minimize the transition band, the more likely there will be ripples. So ripples, the inconsistency of our pass band and stop band amplitude. Okay, so now when we are designing our filters, especially the advanced ones like what we have here, we have to consider uh, we can simply choose, especially in programming, because digital filters can now be done instead of assembling them in parts physically. We can actually do it using programming only. Okay, you can use Python to create your filters. So the default one is the bezel. So it has a very wide transition band. That's a problem. Um, we can improve it using Butterworth filter. So as you can see, it is now more stiff. Okay, but not enough. There's still a huge transition band. And if we want to minimize it further, then we can go for Chebyshev filter. However, Chebyshev filter already introduces ripples, either at the pass band or at the stop band, just like here. Okay, but if you want to take it further, if you want if you want our slope to be more stiff, meaning um, very negligible transition band, then we go for elliptic filter, the most complicated of all. Okay, it has almost no transition band, but the problem is it has now ripples in both the pass band and the stop band. Okay, so basically that's some of the first things that we have to understand about filters. Okay, because our signal enhancement, um, um, depends also or revolves in these basic concepts. Okay, so talking about enhancement, digitally, we can make use of Python, different libraries of Python to do that since we are focusing on digital audio and video. Or we can make use of software called micromodeler. So especially if you are into the mathematical aspect. Um, uh, hmm, Audio, you can use what software is this? Audacity. Okay, so Audacity is highly recommended software for learning audio processing, and of course for producing digital audio. Okay, producing or processing audio, digital audio, and also I think this is CapCut for the video. So in our videos later, we have something about CapCut. Okay, so enhancement. What enhancements can we do? For example, we can cancel echoes. So make use of filters to cancel echoes. Or we can adjust our compression part. So it's no longer about filters. We can adjust the dynamic range. When we say dynamic range, the distance between the highest peak and the lowest peak. So we can either narrow the gap or widen the gap. Okay, so that we can balance the soft and loud parts of our especially of our audio. And speech enhancement for recognition system, so we can filter out other noises, other sounds that come with our voice. For example, there's a, a vehicle that passed by as you talk. So using speech enhancement, it will ignore the sound from the vehicles or any other noise around us. Okay, so actually this is what happens in Zoom. Zoom has built-in speech enhancement now. So I believe my voice is quite clear now, unlike in the previous versions of Zoom that our voice is easily affected by the different noises around us. Okay. Now, in terms of video enhancement, so one of the things that we do is contrast adjustment. So just like dynamic range compression, the comparison between the darkest and the lightest pixels are being narrowed down or widened. Okay, so that our goal is to make the details more visible or better than uh, less visible. Okay, also we can do color correction and white balance. Okay, so especially with the help of histograms. Remember what I introduced a while ago, histograms can be used for these two. And super solution AI-driven upscaling for 4K space. With the help of video processing, you can upgrade your the each pixel of your image so that it can now accommodate 4K displays. Okay, 4K meaning you can have more pixels. So that's what you can do with video processing. Okay, now to make it more, I believe this is the most technical part. So please bear with me. So everything that we're talking about is actually under the context of digital signal processing. So we already mentioned, for example, audio and video processing is just part of it. So we also already mentioned about ADC and DAC. So also we have two analog filters actually before the conversion. For example, from your microphone, there's an analog filter that helps us overcome the tendencies of aliasing. So that filter is called anti-aliasing filter, and remember that's analog. Okay. On the other hand, once we remember the quantized signals, they are like staircase, and we want to reconstruct them. We want to return them to their analog form, meaning we want to connect the dots. Now that we are done with the processing, then we have another analog filter called reconstruction filter. So both of these filters, um, basically, they are low pass filters. Okay. And now, why am I mentioning this? Because digital filters are inside here. Okay, so I don't want to to um. Okay, I'll try to make it quick. For example, we want this shape of filter. Then basically, what we do with the help of our software tools like MATLAB and Micro Modeler, we can just move what we call poles and zeros, so X's and O's. Okay, we just move it around the what we call the Z plane. Okay, If you have the MATLAB or Micromodeler, if you use that, you'll see that as you move these x's and circles, the shape changes. And as stated here, the pole is represented by the x's, while the zeros are the circles. So the poles, sabi dito, move pole to 0.35, peak in frequency moves to 0.35. So um, like here, the peak here. So we just move here around the z-plane to achieve the shape of a filter that we want. Okay, so this is only possible in digital filters. And mathematically, or more technically, our digital filters can be in the form of either an FIR or an IIR filter. Okay, FIR filters in short are like the digital equivalent of our high pass, low pass, band stop filters, the basic filters. Okay, that's why basic din yung equations nila. Okay, whereas if you want a more complex shape of your filter, we go for the IIR filters. And as you can see, same lang. We only have same equation, but we added this term. We have the feedback component. So this is the feed forward component and the feedback component. So since it has a feedback component, it is now more complicated. So we're going to talk about that in a while. But for now, why is it called finite impulse response? As you can see, the response of our filter, of our FIR filter is limited. So it stops here. Whereas the in IIR, the response of the filter is infinite. So it's not ending. Okay, although you can see it's almost zero, but it's never zero. Okay, it's only decreasing, approaching zero, but it's never zero. So that's infinite impulse response. And what we want is something like this. It goes to zero. It's no longer moving up or down. Okay, so that it can be stable. So that's the concept. That's the main disadvantage of IIR. There's an issue in stability. FIR is easy but less flexible. IIR, we can have more complicated filters, but there's an issue of stability that we have to watch out for. Okay, so a little bit about diagrams. They're block diagrams. So this is what I was saying earlier. So both FIR and IIR have these components, these feed forward components. Okay, so this one. But in IIR, we have an additional feedback component. So as you can see, feedback, feed pabalik. So this is nice, but it comes with instability issues. Okay, tendency to be unstable. That's why we have to be careful when we are designing them. Okay, so there are some principles in digital filter design that we have to take note of if we want to achieve a certain filter. Okay, so basically, I forgot to mention these coefficients, the letter B, the B coefficients, and the A coefficients are basically manipulated to come up with a certain shape. So whenever we move the poles in zeros here, the X and the O's, okay, whenever we move them, these coefficients, this B and A coefficients also change. Okay, so that's basically how the digital filters work. It's all about coefficients determined by the positions of our X and O's in the Z plane. Okay, and there's a bit of math in there. Okay, so that's the best way that I can explain this complex, very complex topic. I hope may nakuha tayo maski pa paano. So with all of this in hand, with all this information in mind, we can now better understand feature extraction, or we can now perform feature extraction, which is to convert raw signals into compact meaningful representations that are suitable for machine learning models. If we want to train our algorithms to have to come up with a good model, a usable and reliable model, then we have to make sure that okay ang we are okay with in terms of feature extraction. So, for example, in audio, the features might include frequency patterns such as spectrograms, um, as well as pitch, energy, or embeddings from a pre-trained model. Okay, so in video or image naman, features include edges, the edges of our shapes, or whatever in our image, um, motion vectors, and deep representations from convolutional layers. Convolutional layer, like what I showed previously about 2D convolution. So something like that. Oh, we have an example actually. So here, for example, both audio and video can undergo 2D convolution. So remember the 2D convolution for the images. Actually, we can do that also in images, but if we have spectrograms. So first we have to represent our audio in terms of spectrogram, or in the case of image, it's the image itself. So there will be convolutional processes here, and each output is being fed here in our what we call neural network. So this is our AI model already. In the terms of deep learning, our AI models are represented as neural networks. So specifically, this example is a neural network for classification. So I think what is being classified here is the type of instruments or objects. Okay, and also take note. So I'm not going to talk much about machine learning and deep learning, but in comparison lang. So as you can see, machine learning basically, like what I mentioned in one of the previous webinars, um, we only have one processing or input or processing or hidden layer in the neural network for traditional machine learning. So, but if we have more processing or hidden layers, then it now classifies as deep learning. So, one of the main um, hidden layers that we can add is the feature extraction. So, in the traditional machine learning, feature extraction is done manually. So you have to identify manually what's the pitch, what's the energy of your audio, or what are the details, the images, the edges of your image. You have to manually extract those features. But in deep learning, there's a layer already that does that for you automatically. Of course, meaning the network becomes your neural network becomes more complicated. So anyway, the output could be the same, but uh, in more advanced applications, deep learning will be much better, but more complicated. Okay, so that's all for now. That's all I can give you for now regarding um, um, the AI part or the AI application of audio and video processing. I guess we have more in our last part. Okay, so again, we have another evaluation form. Kindly scan so you can access them. Again, feel free to ask questions and let me know uh, in the comments or even in the evaluation form. You can insert your questions there, and would be glad to answer them. Okay, so while you are watching, you can watch this. While you are accomplishing this form, you can also watch these videos.